Now we are moving to another section, as we have of course finished section 3 of chapter 4. It was about sketching the graph of the function, the procedure for it, and increasing, decreasing functions, and all those stuff that were summed up in that section. Now we are moving to another section, the last section of chapter 4. It is about indeterminate forms and Hopital's rule. Okay, you're already familiar with Hopital and indeterminate forms, most of them, because you have studied this one in the high school. Okay, what are indeterminate forms? Indeterminate forms, I have got infinity over infinity. Okay, when I'm finding, of course, the limit of a function, I get infinity over infinity. I've got 0 over 0. I've got 1 to the power of infinity. I've got 0 multiplied to infinity. I have got infinity minus infinity. Okay, and I think that's all we have got. Okay, these ones are the indeterminate forms that we have got. When we are finding the limit of a function, we will not every time get the result that we want, of course. We will get those forms sometimes. How do we solve those kinds of forms? We will use Hopital's rule, or you will see the procedure for finding the limits of those kinds of functions. The first indeterminate form that we will have is the indeterminate form 0 over 0. Okay, we'll start with 0 over 0. If I have got a function and if I want to find the limit of that function, and if I get 0 over 0, how can I deal with that function? The first example that I have got is x minus, example 1. We have got limit of x approaching to 0, 3x minus sine of x over x. That's the first example that we have got for using Hopital's rule. How do we use Hopital's rule? In general, when we are finding the limit of a function, and if you get 0 over 0, what do we do? What will we do? We will find the derivative of the numerator alone and denominator alone, not using the quotient rule. Okay, not using the quotient rule for finding those limits, but we are using the derivative of numerator alone and denominator separately. Then we will take the limit again to see what has happened to our procedure. Okay, now I have got this one. If I solve this one, what will I get? I will get, if I put 0 into here, I will get 0 minus sine of 0 is 0, so 0 minus 0 is equal to 0, and of course the denominator is equal to 0. Since it is 0 over 0, so what is the indeterminate form? It is that one that we were talking about, so I'm using Hopital's rule. Okay, what does Hopital say? It says take the derivative of the numerator separately and then come to the denominator and find the derivative of the denominator separately. Okay, let's do this one. Now I have got limit of x approaching to 0. What is the derivative of, let me do this one, okay, because I'm doing it separately, not as a quotient function. I don't say first one's derivative multiplied to second one minus second one's derivative times first one. This is the quotient rule. In Hopital, we do not have quotient rule. We are doing it separately, numerator separately, denominator separately. Okay, so what is 3x? The derivative of 3x, it is equal to 3. What is the derivative of sine of x? That's equal to cosine of x. I have got that negative and I put it down there. Okay, now I'm done with the numerator. I'm coming to the denominator. Look, separately I'm taking their derivatives. Okay, what is the derivative of x? That's equal to 1. Now I'm doing the procedure of the limit for that function, for that new function. What does that equal to? If I put 0 into here, it will be 3 minus cosine of 0, okay, over 1. Okay, that will be 3 minus 1, because cosine of 0 is equal to 1, over 1. That's equal to what? It's equal to 2. Okay, so that is Hopital's rule. We are taking the derivative of the numerator and denominator separately. Okay, Hopital is used when we have got indeterminate form. So what are we going to do? We are taking, okay, let me write it for you, taking the derivative of numerator and denominator, both of them, okay? If you're taking numerator, you also have to take the derivative of the denominator. That's important. Separately, okay? Separately, that's important. Okay, let's move to the second example. What do we have? We have got limit of x is approaching to 0, 1 plus x minus 1 all over x. Again, if you put 0 into here, what will I get? I will get 1 minus 1. Okay, that will be 0 over 0. Since again I have got the indeterminate form 0 over 0, so what shall we do? This is the indeterminate form and we are using Hopital's rule. What does Hopital say? It says take the derivative of numerator and denominator separately. What's the derivative of this one? If you remember, we are changing this one to a power, okay? 1 plus x to the power of 1 over 2. 1 over 2 comes in front, and we are taking the derivative of inside, and the power decreases by 1. So in general, we get 1 over 2, 1 plus x to multiply to square root of 1 plus x. Derivative of minus 1 is equal to 0, so I will not write it. And the derivative of denominator, look separately, that's equal to 1, okay? So what is that derivative equal to? I mean that limit, I will simplify it more, x approaching to 0. That one doesn't make a sense here, so I will have 1 over 2, 1 plus x under the square root. If I put 0 into here, that will be 1 under the square root, 1 under the square root multiplied to 2 is equal to 2. So the result of this one is 1 over 2. Okay? Part 3 of that example, I have got limit of x approaching to 0. Okay? 1 plus x under the square root minus 1 minus x over 2 all over x squared. Now, if I put 0 into that function, what will I get? That will be 1 minus 1, that's equal to 0, minus 1 over 2 over 0. Here, if you put 0 into that function, what will I get? As I said, that will be 1 minus 1 is equal to 0 minus 0 over 2 over 0. That will be 0 over 0 again. So what are we going to do? We are using Hopital's rule again because it's the indeterminate form. When we are using Hopital's rule, what will we get here? That will be limit of the function x approaching to 0. The derivative of this one is equal to 1 over 2, okay, under the square root 1 plus x, okay, you know the derivative of this one. Derivative of minus 1 is equal to 0, and the derivative of minus x over 2 is minus 1 over 2. All over x squared, the derivative of it is 2x. As we said, we took the derivative of the numerator separately, we got this one, and we took the derivative of the denominator separately, we got this one. Again, if you look, if I put 0 into here, what will I get? This part will be 1. So 1 over 2 minus 1 over 2, that will again make it 0 over 0. Since it is again 0 over 0, so I'm again using Hopital's rule, okay? So you may need Hopital's rule repeatedly, okay? It is not just using it one time. If you again got an indeterminate form, you're using Hopital's rule again. So finding this limit of x as this approaching to 0, again, finding the derivative of numerator separately, you can calculate it and you will get 1 over 2 multiplied, 1 over 4, okay, because this one, the power comes and multiplies to 1 over 2 becomes 1 over 4, okay, 1 plus x to the power of minus 3 over 2, okay, the derivative of this one is this, minus 0. Okay, why? Because the derivative of this one is equal to 0 all over 2, because the derivative of 2x is equal to 2. Now if I put x into here, what will I get? I will get that will be 1 to the power of this one is equal to 1, so that will be minus 1 over 4 all over 2. If you calculate this one, you will get minus 1 over 8. Since it is something real, or you can say a number, you got something true, so you're leaving it like that, and the result of that limit is equal to minus 1 over 8. So in general, it is okay to use L'Hopital's rule repeatedly. Coming to another example, another part, we have got limit of x as this approaching to 0 of x minus sine of x all over x to the power of 3. Okay, how do you find that derivative? Again, that limit, I'm putting 0 into here. I will get 0 minus sine of 0 is 0, so that will be 0 over 0. Again, what do I have to do? I have to use L'Hopital's rule. What does L'Hopital say? It says find the derivative of numerator. Okay, so that one is equal to limit of x as this approaching to 0. What is the derivative of x? It is equal to 1. What is the derivative of sine? It's equal to cosine of x over x cubed. What is the derivative of x cubed? It is equal to 3x squared. So now inputting the 0 into that function, what will I get? I will get 1 minus 1, because cosine of 0 is equal to 1. So that will be again 0 over 0, because if I put 0 into that one again, it will give me 0. So again, I'm using L'Hopital's rule. That will be limit of x as this approaching to 0. Derivative of 1 is equal to 0. Derivative of cosine is equal to what? Is equal to sine of x. Okay, because the derivative of cosine is equal to negative sine, and I have got a negative sign here, so sine of x will remain here, and that one will be 6x. Again, if you look at this one, again we will get 0 over 0. Since again it is 0 over 0, again we are using L'Hopital's rule. So as we said, it is okay to use it repeatedly. Now, limit of x as this approaching to 0, derivative of sine x is equal to cosine x, derivative of 6 is equal to 0. Now if I put 0 into that function, I will get 1 over 6, and that is the required result. Okay, that was the case where we had 0 over 0. How about if you have got infinity over infinity? We are doing the same procedure. If we got infinity over infinity, we are again using L'Hopital's rule. Okay, let me put it in a box. And I have got the case, that's number 2. Let me just put it in a box. Infinity over infinity, if you found the limit of a function and we get infinity over infinity, we are doing the same procedure. Okay, that means we are taking we are using L'Hopital, and again taking the derivative of numerator separately and denominator separately. Let's come to an example. We have got find the limit of x as this approaching to pi over 2 of secant of x. That's example 4, sorry for that. Okay, over 1 plus tan of x. If we look at this one, we know that secant is undefined when it is pi over 2, so that will be infinity. Okay, and 1 plus tan of pi over 2 is also an asymptote. Pi over 2 is an asymptote for both of them, so that will be pi over 2, infinity over infinity. Since it is infinity over infinity and it is an indeterminate form, so we are using L'Hopital's rule. What does L'Hopital say? It says we are finding the derivatives separately. So that one is equal to limit of x as this approaching to pi over 2. the derivative of secant x is equal to secant x tan x. Okay, the derivative of secant x is equal to secant x tan x. How about the derivative of 1 is equal to 0? Derivative of tan is equal to secant squared of x. So this secant cancels with 1 second. What remains? Limit of x as it is approaching to pi over 2 tan of x over secant of x. Okay, tan x over secant of x is equal to what? That is equal to sine of x. Why? Because tan is equal to sine over cosine and secant is equal to 1 over cosine. Let me write it for you. This one is sine of x over cosine of x, and this one is 1 over cosine of x. That cosine will cancel with that cosine. It will be sine of x, okay, of pi over 2 from the negative side, from the left side. So what is sine of 90 degrees? It is equal to 1, and that is the required result. Okay, the second example, we have got limit of x as it is approaching to infinity, ln of x over 2 root of x. If you evaluate this one, x as it is approaching to infinity, if you put infinity into here, ln of infinity is equal to infinity. Okay, and of course this one is infinity. Since we have got infinity over infinity, so we are using L'Hopital. L'Hopital, again, what does it say? Taking the derivatives separately, x approaching to infinity, ln of x, the derivative of it is equal to 1 over x, and 2 root of x is equal to 1 over root of x. Okay, because the derivative of this one is 1 over 2 root of x. The 2 cancels with the 2, so 1 over root of x remains. What does this one equal to if you simplify? This one cancels with this one, so that one will remain limit of x as it is approaching to infinity, 1 over root of x. Okay, because that one is root of x multiplied to root of x. One root cancels each other, so only one root remains here, and the result of this one is equal to 0, because 1 over infinity is equal to 0. Part 3, limit of x as it is approaching to infinity of e to the power of x over x squared. If I put infinity into that one, what will I get? E to the power of infinity is infinity, infinity squared is infinity. Again, it is L'Hopital's rule. We are taking the derivative of this one. I think this one may need it separately, repeatedly. So that one is limit of x as it is approaching to infinity. The derivative of e is e. Derivative of x squared is 2x. Again, we will get infinity over infinity when I'm putting infinity into there. So again, we need L'Hopital's rule. If I use L'Hopital's rule, again, I have to take the derivatives separately. So that will be e to the power of x over 2, because the derivative of e is e and the derivative of 2x is equal to 2. Now, if I put this one over there, what will I get? I will get infinity over 2 and infinity over 2. The result is infinity. Let's do example 2. We have got finding limit of x as it is approaching to 0 of 1 minus cosine of x over x plus x squared. If you look at this one, what will we get? If I put 0 into here, cosine of 0 is equal to 1. 1 minus 1 is equal to 0, and this one is 0. So I have got the indeterminate form. L'Hopital shall be used. Okay, that's not infinity over infinity, but 0 over 0 is again an indeterminate form. So I'm having limit of x as it is approaching to 0. 1, the derivative of it is equal to 0. Derivative of cosine is equal to minus sine. With that negative, it will make it positive, so that will be sine of x. Derivative of x is equal to 1. Derivative of x squared is equal to 2x. Now, sine of 0 is equal to 0. And this one is equal to what? Is equal to 1 plus... 1 plus 0 is equal to 1. So that is 0 over 1. Is that an indeterminate form? No, it is 0 over 1. So I'm not using L'Hopital's rule for this one. It's 0 over any number is equal to 0. So the result of this one is equal to 0. Be careful of that. Do not make a mistake when you have got 0 over a number, because it's simply equal to 0. It's not 0 over 0 or an indeterminate form. Okay? Now we're coming to the indeterminate forms of infinity multiplied to 0 and infinity minus infinity. Okay, these ones are also indeterminate forms. In example 5, we have got two parts, but I will do only the first part for you, because the second part is again the same procedure as you're doing for the first part. Okay, so I have got limit of x as it is approaching to infinity, x sine of 1 over x. Okay, part B, that is limit of x as it is approaching to 0 from the positive side, root of x, ln of x. Why from the positive side? Because ln of the negatives is not defined. Okay, this one is left for you. It's already solved in the course material. So I'm solving this one. That's equal to what? If I put infinity into here, that will be infinity. If I put infinity in here, that will be 1 over infinity is equal to 0. Sine of 0 is equal to 0. So that will be infinity multiplied to 0. Infinity multiplied to 0, what do we have to find? We have to use L'Hopital's rule. Okay, LH, I'll simply write. Okay, now if I... sorry, we are not using L'Hopital's rule. First, we are doing algebraic operations, then we are using L'Hopital's rule. Sorry for that. When you are having these two cases, first you are doing some algebraic operators to convert them to infinity over infinity, okay, or 0 over 0, okay. Then when we get those situations, then we are using L'Hopital. So in here I have got infinity multiplied to 0. I have to do some algebraic operations. I will simply put that x underneath the sine of x. Okay, that's an easy one. Limit of x as this approaching to infinity. Can I write this one as sine of 1 over x all over 1 over x? Yes, I can write it, because we have already talked about this procedure. I can simply grab this one into the denominator of sine of 1 over x, and I will write it as 1 over x. Why? Because if I will change this one back to its normal face, that division will change to multiplication, and that 1 over x will be x again, and I will have the same situation here. Okay, here, if you look at this one, we had a formula. If I have got limit of x as it is approaching to 0 of sine of x over x, look, this x and this x is equal to each other, and the x's are equal to each other. So that would equal to 1. Okay, here, that will make it 0. Okay, and that one is 0. It is the same procedure as this one, but instead of x approaching to 0, it's approaching to infinity. But here, if you look, instead of x, what do I have? I have got 1 over x. So 1 over x, when I'm putting infinity in here, I will again get 0, sine of 0 over 0. So according to that rule that we have studied previously, what is that limit equal to? It's simply equal to 1. So here, even though we had the indeterminate form infinity multiplied to 0, but when we did some algebraic operations, we didn't need L'Hopital's rule. We could directly solve it. Okay, but in that one, in the second example, what will you do? You will let me do some simple steps for you. Okay, you're changing this one to limit of x as it is approaching to 0 from positive side, ln of x over 1 over root of x. Okay, here what will you get if I put 0 into here? Ln of 0 is equal to what? Look, if I put 0 in here, what will I get? I will get 0 multiplied to infinity. That's this indeterminate form. But when I'm changing it in algebraic operations, what will I get? I will get infinity, okay, over infinity, okay, because this one is infinity, that one is infinity. Now from here you're using L'Hopital's rule. How do you use L'Hopital's rule? A derivative of ln of x is equal to 1 over x. That's done for you in the course material, and you're finding the derivative of this one, you will get the required result. Okay, so when you have got these indeterminate forms and when you are doing algebraic operations, sometimes you may need L'Hopital's rule, like in that example, and sometimes you may not need them. You will just solve it algebraically and you will get to the required solution. Now in example 6, we have got the indeterminate form infinity minus infinity. Example 6, limit of x as it is approaching to 0 of 1 over sine of x minus 1 over x. If I look at this one, or if you look at this one, sine of 0 is equal to 0. So 1 over 0 is equal to infinity. Minus 1 over 0 is infinity. So infinity minus infinity. So before using L'Hopital's rule, we are doing algebraic operations to see whether we can solve it easily or we may need L'Hopital's rule. Here, I'm doing the equalization of denominators. Okay, equalize them. So what will I get when I'm equalizing the denominators? I will get limit of x as it is approaching to 0. I will multiply this side by x and this side by sine of x. So that will be x minus sine of x over x sine of x. Okay, look, x sine of x is the denominator, x minus sine of x. Now if I put 0 into that function, what will I get? 0 minus 0 is equal to 0, and that one 0 multiplied to 0 is equal to 0. So that is an indeterminate form. Here we need L'Hopital's rule, so we have to find the derivative of that function. How do I find the derivative of that function? Since it is L'Hopital, so I'm using them separately, or I'm finding them separately. That will be what? The derivative of x is equal to 1, derivative of sine is equal to cosine of x, over this one is the multiplication of two functions. So we say first one's derivative multiplied to second one, so that will be sine x, plus second one is derivative multiplied to first one, so that will be x cosine of x. Again, this one is still 0 over 0, so we again, why? Because if I put 0 here, it will make it 1 minus 1, 0 over 0. So again, we are using L'Hopital's rule. Look, we had the indeterminate form infinity minus infinity. We did algebraic operation, we got 0 over 0, and we used L'Hopital. Again, when we used L'Hopital, again, we are getting an indeterminate form. So again, you have to find the derivative of that function. Now, when you're finding the limit of that function, I mean the derivative of that function, what will you get? Derivative of 1 is equal to 0, cosine is equal to minus sine. With that negative, it makes it positive. And the derivative of the denominator, sine function becomes cosine function. Okay, and when we are taking the derivative of this one, all in all, we will get 2 cosine of x minus x sine of x. That will equal to what? If I put 0 into here, it will be 0 over, if I put 0 into here, that will be 2 minus 0, and that will be 2. 0 over 2 is not an indeterminate form. It is simply the result equaling to 0. Okay, so when you have got the indeterminate forms, infinity minus infinity or infinity multiplied to infinity, you have to do some algebraic operations to see whether you will need L'Hopital's rule or not. Now we're coming to another indeterminate form. These ones are called indeterminate powers. Okay, that was the fourth one, I think. Indeterminate powers. In indeterminate powers, what do we have? We have got 1 to the power of infinity, 0 to the power of 0, and infinity to the power of 0. Here I have only written 1 to the power of infinity, but I can also add 0 to the power of 0 and infinity to the power of 0. Okay, so we have got these indeterminate forms, indeterminate powers. In order to solve such kinds of examples, we have to use logarithm, okay? Or I can say logarithm, or you can simply use ln, okay, to put the power down and then you evaluate it and see whether you need the L'Hopital's rule or not. It depends on the example that would be given to you. Now the first example that is given to you about indeterminate forms, we have got the example. It says show that limit of x as it is approaching to 0 from the positive side, okay, of 1 plus x to the power of 1 over x is equal to e. So we are dealing with that part. That limit of x as it is approaching to 0 from the positive side, 1 plus x to the power of 1 over x is equal to what? Is equal to, that will be 1 over 0 is equal to infinity, 1 to the power of infinity. Since it is 1 over infinity, so what do I have? I will start with the function. What is the function that I have got? It is 1 plus x to the power of 1 over x. This one has made a problem for me, that function. So what will I do? I will take ln for both of the sides of the equation. Now, when I'm taking ln for both of the sides of the equation, that will be ln of f of x equal to that 1 over x comes in front of the ln. So that will be 1 over x ln of 1 ln of 1 plus x. Now I'm finding the limit for that function. Okay, so that will be limit of x as it is approaching to 0 from the positive side. We are using positive side because ln does not take negatives. Okay, 1 plus x. If I find this limitation, what will I get? That will be infinity. Okay, 1 over 0 is infinity multiplied to ln of 1 is equal to 0. So we have to do an algebraic operation so that we're finding that limit. Okay, so I'm putting that 1 over x underneath. That will be ln of 1 plus x over 1 over 1 over x. That will be x, okay, because I'm taking this one to the denominator. When I'm taking it to the denominator, it will be 1 over 1 over x. Now, if I calculate this one, look, we said when we have got this form, we're first doing an algebraic operation before doing L'Hopital, because L'Hopital we are using it for infinity over infinity, 0 over 0, okay? The others we are doing algebraic operation and then we're getting these ones. Okay, now, if I put 0 into here, I will get 0 because ln of 1 is equal to 0 over 0. Now I'm using L'Hopital's rule. Look what we did. We used ln for bringing the power down. Then when we brought the power down, we got an indeterminate form. We did algebraic operations. We got an indeterminate form 0 over 0. And now we are using L'Hopital's rule. When you're using L'Hopital's rule, what do we have to do? We have to take the derivative of numerator, that is ln, since we have got ln, so the derivative of this one is equal to 1 over 1 plus x, and the derivative of denominator, that is equal to 1. So that limit is equal to what? It's equal to limit of x as it's approaching to 0 from the positive side, 1 over 1 plus x. What is that limit equal to? That's equal to 1 over 1, and the result is equal to 1. What is equal to 1? Of course, limit of ln of f of x is equal to 1. But what am I searching for? I'm searching for limit of f of x, okay, is equal to what? So I have got to find limit of f of x, I have to raise this one with e, okay? I'm putting e in here, e in here, okay? I'm raising this one to e so that I will get limit of f of x. So in general, limit of x as it is approaching to 0 from the positive side is equal to, of f of x is equal to what? Is equal to e to the power of 1, and that's equal to e. Why? Because we found a limit of, look, we found we took ln for the function, okay? And what was the result? It was equal to 1. To find f of x, I have to get rid of that ln over there. To get rid of that ln, I have to raise it with the base of e, okay? Because they are opposite procedures, opposite procedures, opposite functions, inverse functions, and they will cancel each other. So these two cancel each other, and f of x is equal to e to the power of 1. That's equal to e. And that's the result for the limit. I'm leaving example 8 for you. Okay, it's limit of x as it is approaching to infinity of x to the power of 1 over x. Okay, that one is again an indeterminate form. You have to take the logarithm of the function to bring the power down. Okay, let me do the simple steps for you. That will be infinity, okay, to the power of 0. You are taking ln, okay, f of x is equal to what? Is equal to x to the power of 1 over x. I'm taking ln for both of the sides. What will I get? I will get ln of f of x, that's equal to 1 over x ln of x, okay? Now if I take limit of this one, it will be 0 multiplied to infinity. You're doing algebraic of operations like this one, and you will need L'Hopital's rule to solve it. Okay, that's easy and it is done in the course material. That's why I'm not doing it for you, leaving it for you. I hope you would have understood the applications of derivatives as using it for L'Hopital's rule, for limits, for finding limits of indeterminate forms. As we said, we have got lots of indeterminate forms, and we can use L'Hopital's rule to solve them. I hope you would have understood the subject easily. That's the end of section 4 of chapter 4 and the end of chapter 4. Hope you will enjoy watching the mathematics video, and have a good time, and bye-bye.